welcome to Module 20 on support vector machines and margins. By the end of this module, you should be able to explain the geometric idea of a margin and how SVMs, support vector machines, choose a separating hyperplane. You ought to be able to write down and interpret the hard margin and soft margin SVM optimization problems, at least understand what the differences are between hard and soft margins. You ought to be able to relate the penalty parameter C to regularization, margin width, and training error. You ought to be able to describe how kernels combine with SVMs and why only support vectors matter. We talked about kernels in Module 19. And you'll be able to implement and analyze simple linear and RBF kernel SVMs using scikit-learn, including some basic model selection. So recall our linear classifier. This is before feature map space, transforming features into higher dimensional nonlinear spaces, is just the weight vector, or the parameters w times x plus a bias term b, and we're just looking at the sign, right? So if the sign is positive, it's a positive class. If it's negative, it's a negative class. So many different parameters, w and b, will perfectly be able to separate the same data, and logistic regression will pick the parameters using maximum likelihood. We've framed this previously, mostly in class, as related to cross-entropy loss. But among all the separating hyperplanes, we have to pick one in many cases, but there might be many or an infinite number of them. Here's just a simple example of this. These are two very distinguishable classes, purple and yellow, and we have a linear boundary between them. I've drawn three of them, dashed orange, dashed blue, and green. But you can tell there's you could tilt this an arbitrary number of ways and still completely and perfectly separate purple from yellow, given this training data. So given these infinite number of possible linear boundaries, which one is the best? So the key thing to remember is that we want to choose the separator, the linear boundary, in such a way that we'll be able to do a good job on future unseen events drawn from a similar distribution that produced the training data. So if we're going to keep on drawing purple circles and yellow circles, those circles are going to be drawn, those points are going to be drawn around these kind of clusters, but not exactly at these exact points. So you might have the occasional purple dot, which is a bit closer to the yellows, the occasional yellow dot, which is closer to the purples. It'll be kind of a cloudy sample around what we have already. And if that's the case, we want to make sure that those previously unsampled data points will still be classified correctly. So to do that, we want to choose a margin, a barrier, like a border between these two categories, so that when we're sampling new purples and new yellows, we're still likely to keep those points on their respective sides. So we have this geometric, or like an image-based picture of a margin. So still, we have this linearly separable data, and the labels are going to be just positive and negative. So y is positive or negative. We have a linear classifier as hyperplane. So again, a hyperplane is just sort of a plane in higher order dimensions. This is what we mentioned a moment ago. The margin we're defining now is the distance from the hyperplane to the closest points on either side of the hyperplane. And the points that lie exactly on the margin we're defining to be the support vectors. This is probably best seen as an image. So here we have two categories. Now the categories are blue and orange. Here's our training data. The ideal boundary we've defined is this thick black line in the middle. This is our class boundary. The margin is essentially the distance here, orthogonal to the hyperplane, so at 90 degrees from the hyperplane, kind of towards the blues in one direction and towards the oranges in the other direction, to an equal amount. And then we kind of bump up against these data points here, which are circled in red. These are the so-called support vectors. These data points are vectors, so technically, even though these are two dimensions, even two-dimensional points are little vectors, but this generalizes to much higher dimensional data. And they're called support vectors because they kind of support the margin. They kind of hold up the margin. You can see, especially down here, like as you draw your linear boundary and then move the margin orthogonally away from the boundary, eventually you're going to bump up to these data points, and you want this to be as wide as possible. It's going to be visualized a little bit later, but you can imagine sampling new blues and new oranges, and they're going to not necessarily always fall behind where they were previously. Occasionally, some oranges are going to skip into the neutral zone over here, into the margin, but still be on the correct side of this decision boundary, if that makes sense. So we want to be robust against future samples from the same classes, and this is an ideal way of doing it, is to make as big as possible a neutral zone between north data area and south data area as we can. So again, this is the main point. Instead of just separating the classes, which we could have done in an infinite number of ways, we want to maximize the margin to minimize the risk of newly sampled points finding themselves on the other side of the wall. So that was geometric. Let's talk about the kind of functional representation. For a labeled data point x sub I, y sub I, and y sub I is again binary, positive or negative, we have this functional margin, which we're going to call gamma sub I, which is defined here. This is positive if it's labeled correctly, if it's correctly classified, and negative if it's misclassified. And it's going to be scale sensitive. So if you scale our parameters w and b by some amount alpha, this will also scale gamma by alpha. You can see that you multiply w and b by some alpha, that alpha pops out of these terms, out of this parentheses, and it will change gamma by an amount alpha also. So the geometric margin, the signed distance to the hyperplane, is defined this way. We have, gamma hat I should have said. So gamma hat here, we can normalize by the norm of the weight vector. So here's gamma sub I. This is equivalent to how we've just defined it up here as y sub I times this prediction. We just normalize by the norm of w. Doing so means that the margin gamma, it won't change if we rescale w and b. We don't want it to change if we rescale. So if we move w and b by some positive factor, the hyperplane won't move at all. It'll be the same classifier. So a true geometric margin should stay the same under that rescaling. So we care about this geometric margin of each point, gamma sub I. Each gamma sub I is the signed distance of point I to the hyperplane. And we want to find the smallest of these distances, which is the worst case margin. So gamma sub I is defined on for every point. So this is sort of the distance of data point to the margin, to the hyperplane. And we want to figure out which ones are the closest. These are, out of all the data points I, we get some distance gamma sub I, the normalized distance gamma sub I. Which one of them is closest? This is going to be defined as gamma. And our goal is to choose the weights we can change, and weights in w and b, the parameters, to make this worst case distance as large as possible. Okay. So in other words, we have all these data points in our training set. Some of them will be very close to the decision boundary. They'll be very close to the wall, so to speak. And these points are tricky points, right? These points are the more similar to the opposite class. So they have the smallest distance to the margin. And these are the most likely, because they're so close to the margin, to fall within this neutral zone. They're in the danger zone, if you want to think of it that way. They kind of represent how close one side is to the wall, and we want to stay as far away from that wall as possible. So we have, I'm kind of hinting at the fact that I'm thinking of this in terms of, like the Berlin Wall separating East and West Germany, or you can think of this as the boundary between North and South Korea, or in those kinds of terms. It might help to think of it in those terms. You have a strict boundary, extremely strict. You have members of each of those countries, and getting too close to the wall in either side could potentially be dangerous. So you have some members of your society which are kind of getting closer and closer to the wall. Those individuals are at risk. You want to keep them as far away from the wall as possible. So find all of the individuals who have the minimum distance to the wall. That's what we talked about a moment ago. This is our gammas. And we want to keep the people who are closest to the wall as far away from the wall as possible. This might be kind of confusing because we're talking about minimums and maximums at the same time. But you want, again, the individuals who are closest to the wall to be as far away from the wall as possible. And that's how we're going to define where the wall is. In other words, the settings for our decision boundary, W and B here, the parameters we're allowed to change. The best ones are W star and B star. This one says, well, pick W and B such that we're maximizing the minimum distance, right? So whoever's closest to the wall, keep them as far away from the wall as possible. I hope that makes sense. I put a box around this equation because it's relatively important. So if you don't understand, I mean, some parts of this might be more or less important than others. I think the main point is just like we're maximizing the distance between the wall and the individual's data points that are closest to the wall. That's this box. And we're doing so, through this normalized term. So we're normalizing everything based on our parameters. So we don't want to, we don't want to change the decision boundary based on scaling our parameters. So the hard margin SVM, this is the completely separable case. This is the idea that we have data that are completely separable. There's no, East Germans on the west side of the wall. There's no West Germans on the east side of the wall, so to speak. Everything's entirely separable. This is the hard margin case. We can write the problem down in terms of the geometric margin, and this is more or less what we had a moment ago. So we have this max gamma, and all of our distances of our data points normalized by the weights has some positive value. Okay, so all of the points on our side of the class are on our side of the wall. Because if we scale our parameters W and B by some positive constant, this should not change the classifier. We can rescale everything so that the closest points satisfy this equation. Y sub I of our, Y sub I times this prediction is equal to 1. And with this convention, the geometric margin, because of how we've defined it here, that just becomes 1 over the norm of W. And then that means that the problem will be equivalent of minimizing these functions. So I've plugged in basically gamma. I've replaced it with 1 over omega squared. Maximizing gamma is going to be the same as maximizing this fraction over here, gamma of 1 over the norm of W is equivalent to minimizing the reciprocal of this fraction, minimizing the norm of W is equivalent to minimizing the 1/2 of the 2 norm of W. So with a loss of generality, we have this equation. Minimizing the norm here will maximize the margin, and the constraints that we have will enforce that all of the training points are on the correct side, with the margin being at least 1. Again, just making things a little bit more visual here. Our goal is to visualize how C affects the margin and the support vectors and the performance on a nearly separable data set. So we have these two-dimensional blobs. There's no overlap between them. You can draw a line between them without having any... so the nearest points to the boundary are on the correct side. And we're going to look at different values of C with a linear kernel. We talked about what a linear kernel was in Module 19. And we'll always use feature scaling. We talked about the reason we wanted to use standard scaler in Module 19 also, inside of a pipeline. Nothing very much fancy is happening here. We have 250 samples, 2 centers. Here we're making the blobs. Here we're splitting them by train and test. And here we're just plotting them. So that's our data we're dealing with. Now we have different possible values of C. So remember, C is our sort of a hyperparameter, which we're going to see in a second. We have a couple of different values for it. We're just going to do a grid search over their values to see which one is the best. For all possible settings for C in this list, we'll make our pipeline. The hyperparameter is provided to our SVM with a linear kernel. We do the fit, we do our accuracy evaluation, we do our validation accuracy computation, and we just kind of store like information about what was the value of C, what was the training accuracy, what is the validation accuracy. Oh yeah, and what were the number of support vectors? So the support vectors are the vectors that are the closest to the margin, that kind of support the margin from either side. And then I'll just kind of show it. So this is a very pathological case here. Here, when we're changing the value of C, we're going to get 100% training accuracy and 100% validation accuracy. So this is a very uninteresting case because, you know, the very simple scenario we've constructed is also kind of uninteresting. This is a super like pathological case of classification. It's super easy. It's barely an inconvenience. So it's very easy to get 100% training accuracy and 100% validation accuracy. What's different here is the number of support vectors we end up with. So you'll notice when we have C being set to 0.1, we have 18 support vectors. Those are points that are on the margin. But as we increase C all the way up to 100, we get fewer and fewer support vectors. So we'll talk about why that is in a moment. Here's just a visualization of what we're doing. Copy and paste this yourself. Again, it's a linear kernel, so the decision boundary is linear. Here are our data sets and our decision regions. I've circled the support vectors here in black. So not all of these data points are circled, but you can see that these vectors have been chosen as being somewhat close to the decision boundary. So with a technically, this is a soft margin linear SVM, so we haven't really talked about the soft margin yet because hard margins don't really care about C, but you can get a sense of what's happening. So the training and validation accuracy are identical and they're perfect, but changing C results in some differences. Small values of C mean you have a lot of support vectors, there's a wider margin that leans on a lot of points, and a larger C means there's fewer support vectors. This is a tighter margin that depends only on a small number of points. I mentioned in Module 19 this sort of mnemonic to remind you of some of the hyperparameters we're dealing with when we're dealing with kernel methods, what bigger values of these hyperparameters mean with regards to overfitting and underfitting, what lower values of these hyperparameters might mean for overfitting and underfitting. So you remember what I discussed in that module, and you can apply it here. This is a perfectly separable data set. So changing C basically just means how we separate the classes, not whether we separate the classes. And we're also actually getting ahead of ourselves a little bit because, as I mentioned, C is really helpful when we're talking about soft margins, which we'll talk about in a second. In this next example, example 2, we'll see how C is actually used to trade off training and validation accuracy. So here we have this soft margin SVM. This is more realistic, and it's usually the default way that we do training with libraries like scikit-learn. In real data sets, the data are very rarely linearly separable. Even in this class, even in the very simple examples we've seen previously, often elements from each of the classes we're dealing with will kind of end up on either side of the border. They'll be mingling with the enemy on the other side. There might be noise from measurements. There might be noise from just the data generating process itself. There might be outliers. Maybe the classes themselves just overlap. Maybe whatever separates these classes is not really visible in the data we have. All kinds of problems with data overlapping. To some extent, the kernel trick, using feature maps to raise the data we have into higher dimensions in which classes might be linearly separable. That's one way of dealing with these problems, but that doesn't always work, especially if we only have a small handful of kernels we're dealing with. Anyway, to solve this problem actually, and even in the previous example with a, quote, hard margin classifier, we're secretly doing soft margin SVMs. We will introduce the idea of a slack variable, xi. It's pronounced xi because this is a Greek letter. So it's written like she. The slack variable xi sub I being greater than or equal to 0 gives us this new term. So we still want to try to minimize this norm of the W, such that we maintain the like prediction accuracy. So just like we mentioned earlier, this will give us positive scores if it's correctly classified. So we want all the classifications to give us positive values here. And this again assumes that the positive class is plus and the negative class is minus, and we have a decision boundary of 0. With this product. Anyway, we talked about that before. So we have the previous decision boundary. We want to try to minimize. We pick W and B to minimize this actual setting for the weight vector. We also add this new term, the slack variable. We introduce C, this hyperparameter, and then we have this value xi sub I for each of our data points. And we have this, this new term here. We have our prediction. We want it to be positive. We want it to be greater than or equal to 1. We subtract this slack variable xi, and xi should always be greater or equal to 0. So if xi sub I is equal to 0, this means that the point is correctly classified, and the margin is greater than or equal to 1. If xi falls between 0 and 1, this means that the data point is correctly classified, but it falls within the margin, or within what we call the neutral zone between the two nations. And if xi sub I is greater than or equal to 1, this means that this data point has been misclassified, but we kind of still allow it. It's just not not ideal. So we want to try to minimize the chances of these data points being misclassified, but it's still possible. Okay, so again, this first term is the one that allows us to set the slope of our decision boundary, and we set it in such a way that we can maximize the margin. So this is essentially maximizing the margin. And we also allow for some of the data points to either be in the margin or on the wrong side of the decision boundary. So we allow for the fact that we're misclassifying. We can misclassify some data points, and we want to minimize both of those things. We want to maximize the margin by minimizing this amount, and we want to minimize the number of misclassifications we're making. And we can, just like we saw previously with extra terms being used for regularization, we have this hyperparameter. Then it was lambda, now it's C, and this allows us to determine how much we're weighting this new term. Large values of C means we penalize violations very heavily. So this new term is very important. So big values of C means violations are heavily penalized, which results in a narrower margin and fewer training errors. Small values of C allow for more violations. It's okay to have a margin being very big, but then that results in some data points being in the margin or on the wrong side of the decision boundary. This is essentially doing more regularization. Digging a little bit deeper in something called the hinge loss. This is only an aside. You don't need to know this, but for those of you who are interested in machine learning and want to dig a bit deeper, the same soft margin SVM can be rewritten using something called the hinge loss, which is described in this paper from the Preeminent Neurips conference. We have this loss called the hinge loss. Again, just like any loss we've seen, this is like a difference between targets y and predictions f of x. And this is going to be the maximum of 0 and 1 minus y times f of x. And this, again, this is a binary classification task. And f of x is our simple linear function like we've seen many times already. So intuitively, this hinge loss is this convex margin-based surrogate for a binary classification loss that will penalize misclassified points and also correctly classified points that lie too close to the decision boundary. This is the objective. We're just trying to minimize, we're choosing W and B to minimize this overall function. We have the same first term as before, and we have this other term, which is C times the sum over all of our data points of the max of these quantities. If this goes negative, then we get 0. Otherwise, we get whatever this positive value is. So anyways, this is from the paper. This is not stated here, and it's stated, but it's not going to be proven here. For every example you might have, this hinge loss is this upper bound on the binary loss for misclassification. And this makes, therefore, this makes SVM training a convex optimization problem that's still faithful to classification performance. So we kind of hinted at the fact in module 19 towards the end that using these kernel matrices is just a representation for the squared loss plus the L2 regularization loss. This hinge loss from this paper from the 1998, framing this kind of loss in terms of like the class times the prediction in this way, and just reframing things a little bit, means we get the same objective that we just defined a moment ago with a soft margin SVM classifier. And because these things are equivalent, SVM training, or because kind of equivalent, because this hinge loss is an upper bound on the binary classification loss, SVM training is a convex optimization problem like we have been aiming towards from the very beginning of this class, and we become very happy. So here's the support vectors. This is again an aside for those who are interested in it. There's this other paper from the 90s in machine learning, the Machine Learning Journal, which you can read about here. So if you derive the dual of the SVM optimization problems, you obtain this function here. This bracket x sub I x is just the kernel function on these two data points. Y is the label for the data point we're dealing with currently, and so on. So currently being within this sum. As long as alpha sub I is greater than or equal to 0, then this SVM problem the dual of the SVM problem becomes this. The intuition is in the dual formulation. We can rewrite the optimization problem in terms of one weight per training example. So every training example gets a little weight at the optimum. Most of these weights are going to be 0. Most of these weights are not going to be relevant to doing classification on new data points. So here, x is some new data point you're trying to do inference on. You have n training data points. And then you end up learning this new parameter alpha sub I, 1 for each of our training points. Most of these are going to be 0 or very close to 0. That means that the classifier can be expressed purely as a weighted sum of the inner products of a small sample of training points. And these are our support vectors. So just like a moment ago here, you have all of these training points purple, all of these training points yellow. All of them are being used to, in some sense, all of them are being used to define the margin, but really only a small number of them are close to the margin and define its extent, right? So when we're talking about the dual case here, and you learn these parameters alpha sub I, a lot of them are going to go to 0, which means we kind of ignore those terms entirely, and we're just doing the sum over those data points in the training set for which alpha sub I is not 0. And in some sense, those points end up supporting the decision on their own. It's a small, tiny little subset, and these can be framed as the support vectors. And this representation, actually, I should rephrase this. This representation, I say, is what makes the so-called kernel trick possible. The kernel trick is possible regardless of whether we're using support vectors. You could, in theory, have a bunch of alpha sub i's that are not 0 and still use the kernel trick. So this last sentence might be a bit of a misrepresentation, but it makes using the kernel trick feasible, maybe is a better word, because we've reduced the problem into a sum over a very small number of subsets. So inference will be super fast when we're doing predictions on new data points. So the key properties here, again, this is an aside. So again, if you really care about this, and I hope some of you do, you can go ahead and read this paper. Only the points with alpha sub I being bigger than 0 will influence W. These are kind of the support vectors. Most of the training data points will have these alphas close to 0. And classification of a new data point will depend on a weighted sum only of a small number of support vectors, which makes SVMs extremely fast and to some extent powerful. So SVMs and kernels, we can go all the way back to the previous module, module 19, and have this little twist. So we have this inner product x sub I and x, the thing we're trying to predict. X sub I is a member of our training set. We replace this inner product with a kernel. So here our kernel is, a feature map of x sub I into a higher dimensional feature space, a feature map of x into a higher dimensional feature space using some like non-linearities. Then this function x is a sum over our support vectors, of alpha sub I times the sign of the class times the kernel, which we've defined a moment ago, plus some bias b. Again, we never need to actually explicitly construct or compute phi sub x, or the big feature map big phi of x. We can just compute a couple of kernels. We can even compute these on the fly. So every time we see a new value of x, we can put this into our kernel function. We have x transpose times x. Actually, some of these should probably be, x transpose times x prime. The polynomial of x and x prime is the transpose of x times x prime plus beta to the power of d. These are hyperparameters. We've seen these kernels before. So the role of the margin in feature space defined by phi. SVM basically will maximize the margin. So we convert all of our data into a higher dimensional feature space. This is implicit through the use of the kernel. We compute W and B through our training data. We get our support vectors. Then given those support vectors, we get a new data point. We use those support vectors and the alphas we've learned and the labels we have already on our training data to compute this function. This gives us a new prediction for the class, or for like a value that gives us our class, positive or negative, and we're done. So the choice of the kernel will change the geometry, and this therefore which margins are possible. We talked about this in a previous module, but different like linear will just give you linear boundaries. Obviously, RBFs we've applied to the 2 moons example in module 19, which is a very different geometry, like the decision regions. Different kernel shapes, different hyperparameters will give you different decision boundaries, and those decision boundaries translate to the support vector machine, which is making its decisions for us. Let's go back to the moons exercise. So once again, we're going to see the 2 moons, and we're going to see the RBF SVM. In this example, we're going to train an SVM with an RBF kernel on a noisier 2 moons data set, and we're going to play around with C and gamma and change the decision boundary and performance in a way we couldn't really do it before. So we're always going to scale our features before using SVMs, and we're going to treat these as hyperparameters to tune. We're not going to just guess them. This should be obvious by now, but just to mention it, we're just not going to randomly guess hyperparameters and use them. I mention that actually because I see that quite often. Students and even in research papers I have to review. We'll say, well, using C value of this and gamma value of that, these are our results, and they never explain have these been optimized in any way? And usually there's no way to answer that question given the small amount of information we're given, which is a big problem if you want to do machine learning correctly. You have to always state your assumptions or show that your hyperparameters have been optimized in some way. Regardless, here we make the data set with a certain amount of noise. We split with a test set size of 30%. Nothing much to say. We've seen this kind of data before. Now, like we saw previously, we still do a little grid search. We have C's and gammas now. We're just going to do a grid search over them. So for all possible combinations of C and gamma, we make our pipeline. We scale using the standard Z-score. We do our RBF kernel. We provide our current chosen C's and gammas. Fit, get our metrics, and see what happens. And then now we can see something a little bit more interesting. We can see our C's going from 0.1 to 10. We have a few different gammas, and we get much more interesting accuracies. We'll talk about evaluating these in a moment, but you can kind of see you have training accuracies that go down to as low as about 85%, and validation accuracies that go down to as low as 83%. And then, like we saw earlier, we have different numbers of support vectors for each of these combinations of hyperparameters. Here's the decision boundaries. So actually, I think in a previous here, we're where are we? Storing our favorites. Okay, yeah. So we're sorting the values by the validation accuracy. Again, this is like a validation set, so we can go ahead and do this. The highest validation accuracy we have is 96.7. So the values of C and gamma that gave us our best validation accuracy are C equals 10 and gamma equals 1. Good. So those are the ones we're using here. Actually, we're just grabbing them. Anyway, this is where I grab it in code, so there's no risk of error. Regardless, we once again just fit, so we can draw things here. Here are decision boundaries between the purple class and the yellow classes. And there are errors being made, as you can see, obviously. So some yellow points have been misclassified as purple, even in training, but that's fine. We're using a soft margin with the C function applied to the the sum over all of the X's, which is our misclassification loss term. So you can notice a few things, mostly from the table we saw a moment ago. We have excellent training accuracy and high validation accuracy across all of the examples we've found, all of the settings of C and gamma. This means we have a generally good margin in feature space, so everything's looking pretty good. Some settings have a very high training accuracy and somewhat lower validation accuracy. I welcome you to go ahead and try to find them yourself and ask yourself if this is an example of overfitting or not. Some examples have very low or very low, very in quotes low training accuracy and very low validation accuracy. So both training and validation are relatively low. This might mean that the margin is too wide. Maybe the kernel is too smooth. Is this an example of underfitting? So think about it a little bit. This is really just for your own exercise to try to remember what overfitting and underfitting are and try to frame those within the context of margins. And also, diagnose those problems in terms of the relationship between the highness and lowness of training and validation accuracy, which we talked a lot about in the bias and variance module. Our overall design lessons are these. You can always scale the features before SVMs, especially for RBFs. I'd recommend you go back to the code and remove scaling to see what happens, if anything. I should also mention, sometimes we have these pathological training sets from scikit-learn, like the 2 moons, in which removing something as important as scaling might not give you a drastic change in your results, but you should still see some change in results that is at least obvious, if not drastic. And just know that when you're dealing with real data, and you're removing something like scaling, something as important as scaling, you will, in practice, usually get much more drastic changes to your metrics. Here we're kind of changing C and gamma. These are hyperparameters. You need to tune them by validation or cross-validation. Here, we're not using test sets. Like I've just kind of taken all of my data and called it training and validation. And I've imagined that there's some other test set out there that I haven't touched yet. I have to make that clear that I'm not doing the bad thing here by doing lots of experiments, looking at my test set and then choosing C and gamma on my test set. I'm assuming that I'm still kind of only looking at the data I have in my so-called training set, and I've held out some of it for actual validation, not for testing. And then finally, we can use accuracy and support vector counts as qualitative signals. The more support vectors you have, the more support vectors means that you have like a more complicated decision boundary. I call the decision boundary wiggly. So you might see a more like complicated decision boundary. And if you have a more complicated fit, this usually means you're overfitting. Like you think back to regression where you had relatively complicated fits to the training data. It was much more complicated than a smooth function. Wiggly boundaries, more complicated boundaries, similar in scope to complicated regression fits. This means overfitting. Here's another anti-example. SVMs are pretty robust, and like for the longest time, if you're dealing with small data sets, using SVMs can provide a very strong baseline. You might be inclined to do something fancy with like a supermassive deep neural network, but for many cases, using an SVM with a nonlinear kernel, like a radial basis function, will do a lot for you for free. So consider a noisy data set. Maybe add more noise to the 2 moons, or choose a different data set and add noise to that. Try choosing massive gamma, which will give you a very local kernel and a very large value of C. What you're going to see probably is a decision boundary that becomes extremely wiggly or complicated, which will twist around every point that's noisy. Sometimes that won't necessarily be possible, but you can imagine in something like this, the decision boundary here, I hope you can see my mouse, but kind of curling up here around this yellow point and then curling back down to where the kernel was before. And that's what I mean by wiggly. Like instead of having this nice smooth looking, single cavernous little concavity over here, you'd have all these little like tight little carve-outs carving out yellow for the yellow side, is what I mean by wiggly. So yeah, if you add a lot of noise, make gamma massive, make C massive, you're going to see this kind of behavior. Almost every training point will suddenly become a support vector. Training accuracy will get bigger. It might even go to 100%, but the validation test performance will plummet. So you'll see a table like we saw before, but you'll see this kind of diversion between the training accuracy and the validation accuracy. This will violate the spirit of the maximum margin. So the maximum margin, again, we want as big a space between the categories. We want to separate them out as much as possible. We want to have as few as members of our classes as possible being what we call close to the margin. These are the things we're trying to minimize. Minimize the number of points that are close to the margin. Minimize the number of support vectors we have equivalently. And you can do that by maximizing the margin as much as possible. So keep most of the data away from the margin. So again, keep that margin as big as possible. If the margin is big, that's good. But if we have lots and lots of support vectors and a decision boundary that really gets close to all of these support vectors, which are now more numerous, our margin's going to get smaller and smaller. And that means that we're going to sample new data points we've never seen before, just based on the data we have already. And those data points are going to be all over this smaller and smaller margin that we're fitting. The classifier will be brittle to small permutations. That means high variance, and that means overfitting. The moral of the story, I should put this into a little box. The moral of the story is that support vector machines aren't magically robust. So even though support vector machines tend to be robust, you'll do a lot of experiments, and SVMs, you will usually have very good performance. But if you're unreasonable and you pick silly values of C, or if you don't optimize C using a held-out validation set, or if you have other kernel hyperparameters, so the order of the polynomial, if you're using a polynomial kernel, for example, as a kernel hyperparameter, if you don't optimize that on your train and validation sets, then you're going to have a bad time. In other words, the moral of the story is SVMs are not magically always going to be robust. You still have to do the empirical work always. So a couple of extra things. So when we are evaluating SVMs, this applies to other classifiers, but again, it applies here in particular because we have this kind of novel classifier that's different than our logistic regressions. If you have binary classification problems, accuracy can be okay, but if you have imbalanced data, so if you have 90% of your data is positive and 10% of it is negative, or vice versa, you might consider different metrics. So go all the way back to module 12 if you're in that situation. This is true of classification generally or theoretically, but it's also true of support vector machines. You always have to use proper splits, so use training, validation, and test. You can use k-fold cross-validation from module 13. Why do you need that? I mean, you always need this. Generally, it's a good idea just to hammer this home. You should do machine learning properly. But we saw a moment ago that setting C in gamma, for example, can have a huge effect. Well, huge. This particular example was all the values are pretty high, but you can still see there's differences on the order of several percentage points, which if you have high performance, these differences of a few percent can be relatively high. Regardless, if you don't have good settings for hyperparameters, you can have, quote, massive relative differences in performance. So we have held-out validation to allow us to optimize those hyperparameters. Avoid leakage whenever possible. So Scaling has to happen on the training data, so don't apply scalars using information from your test set. Hyperparameters also need to be within the training validation pipeline. The test set is totally sacrosanct and we're not going to touch it until we're actually doing evaluation. Always check for overly complex models. You can do this by just doing those visualizations. This is a lot easier when you have just two-dimensional data like the 2 moons data set. But if you have and what even counts as high C or extreme gamma, like the values of C and gamma and what means high or low in those cases will depend on the data. And if you're dealing with a new data set, then you have no prior knowledge about what C and gamma should be. When you can do your computations, you'll get your number of support vectors, and you'll see that certain directions of changing C and gamma will change the number of support vectors you have. The more support vectors you have, the more complicated the model, and then the more risk you have of overfitting. So you can kind of visualize things in those terms. So always check for how complex the models are, and remember the concept of underfitting and overfitting. We're actually going to dig deeper into underfitting and overfitting with neural networks a bit later, but this just hammers it home a bit more. Always check. I should mention also that what constitutes a high number of support vectors can also be dependent on the data. So you can't just see that, the number of support vectors went from 2 to 20, that means that the latter case must be overfitting. 20 might still be a small number of support vectors for certain, arrangements of data. So you might not have prior knowledge of that either. The proof or the evidence is normally going to be in the divergence of training and validation performance. I also want to mention this again, in case it hasn't been clear already. Often you're going to see work in the real world or research papers, even by highly cited papers or really smart people, in which they're just choosing hyperparameters to be values that appear reasonable. So often you see papers where values of C are something like 0.1 and that's it. And they don't do any modification or hyperparameter optimization. They just leave it because, so-and-so used C in their research, so we're going to use the value of C of 0.1 in our research. They use 0.1, we'll use 0.1. But that's ridiculous, right? Like they use a different data set and than we're using, presumably. So there's no reason to think that their value of C on their data set will translate to the same value of C working for our data set. You always have to do the hyperparameter optimizations. Again, a lot of reviewers are savvy to this and will raise it as a concern. But it's just sort of like doing kind of blindly just taking hyperparameters and reusing them. Unless you're doing a reproducing exercise and you're trying to reproduce other results with everything else being equal. If you're just blindly taking hyperparameters without being inquisitive or curious, then you're cutting corners to an extent that reveals laziness and not much else. SVMs are also subject to this bias variance trade-off, which we talked about in module 14. Here, the bias variance trade-off rears its ugly head through the margin, but all of the high-level wisdom that we learned in the bias variance trade-off with regression translates almost one-to-one in binary classification and in SVM classification in particular. A bit more curiosity. We actually dug into a lot of curiosity that you might kind of put aside, but again, for those who are interested, this is a historical note. SVMs used to be the state of the art for many tasks before deep learning. So I cite text classification here. This goes way back to '98. This is even before my time as a student. But even as I was a grad student into the 2010s, SVMs were still hard to beat. Even relative deep learning neural networks, and when I say deep learning, I mean neural networks with 2 or 3 hidden layers, would still lose on classification tasks to SVMs in many cases. And that might be the case for you if you have a small kind of coarse data set. A lot of real-world data sets are pretty coarse and pretty small. You don't have to leap into using a massive GPU intensive neural network. SVMs might do the trick for you well, and there's no shame in that. And as I mentioned, it's still widely used when the data are medium or small-sized. If you have tens of thousands of data points, sometimes SVMs are still the right choice. If you have engineered features are actually going to come up in the future. But if you have, like, computed features on the raw data, sometimes those can be useful. They're more useful to SVMs than they might be for neural networks. Neural networks so to speak, getting raw data. SVMs implicitly liked taking data and then moving them into a higher dimensional nonlinear space using kernels that implicitly use these feature maps. So instead of using only these nonlinear feature maps, why not also use feature engineering, these kind of pre-computed features? We'll talk about that in module 23. I'm getting ahead of myself. That being said, so SVMs used to be really cool, and SVMs can still be useful when you have certain conditions in real-world machine learning tasks. So don't throw away SVMs just because there's a lot of good music from the 80s and 90s. So why not don't not listen to music from the 90s just because it's from the 90s. Still use SVMs even though they were popular in the 90s. The same concept applies here. Kind of. Anyway, I'm getting off track. Back on track. There are connections to modern deep learning. This margin-based idea, so the core concept of just trying to maximize the margin, between two categories, and the margin is kind of defined as the support vectors. This comes up a lot in modern deep learning. So there's a paper, from 10 years ago now. This is less and less recent, but again, going back to 2016, a lot of concepts stay with us. So we're still using convolutional neural networks. Large margin softmax for convolutional neural networks in this paper in particular is a good representation of margin-based ideas being applied in neural networks. And I think I mentioned this actually in the previous module. Kernel methods generally connect to Gaussian processes, kernel PCA, neural tangent kernels. This is from older work, but is still relevant today. So we'll actually talk a little bit about PCA and neural methods in the near future. I wanted to highlight here, just in practice, you're going to get all these notebooks anyway, so I don't really feel like I need to go too much into the practical aspects of Python and the theory modules, but scikit-learn has a pretty robust implementation of SVM classes. There's SVC, there's linear SVC. This is useful for high-dimensional sparse features. SVR is support vector machines for regression, R for regression, C for classification, and linear SVR is linear SVMs for regression. SVC, like we saw several times, you can apply with various kernels. You can apply it with a linear kernel or a nonlinear kernels like polynomial kernels. And I mean, here, this is interesting. So look at this code. We've seen this code many times before, so I don't feel I need to get into it very much, but we've been making pipelines a lot. Pipelines are helpful ways of making your code reproducible if you're using scikit-learn. Pipelines will come up later when we use Hugging Face. Hugging Face also implements pipelines, which implement the same idea. We want things to be consistent. In this case, we're just doing a standard scalar followed by the actual model with hyperparameters being set and so on. For some reason, this code drew this little box at the bottom here for me. I'm not sure why exactly, but you can run this code yourself, and you can kind of play around with this nice little visualization for our setup. In summary, SVMs choose a separating hyperplane by maximizing the margin between classes. The soft margin balances two things. It balances the margin width. We want the width to be as big as possible. We do that by minimizing this norm of W. It balances that with the misclassification loss. These are violations to the margin. Classes are on the wrong side of the margin. We talked a little bit about the hinge loss. That's kind of a little bit of an aside, but we basically implemented it as something that looked like a regularization. It was a sum over all of our data points with this error term xi, this wiggly looking E-shaped looking thing, which basically tells us that we're making mistakes. So we're balancing maximizing the margin with minimizing the errors. In the dual, only the support vectors will matter. This enables the kernel trick. This practically will just mean that the support vector machine is very efficient. Our hyperparameters can strongly affect the shape of the margin and the number of support vectors we're using, and both of these things, like if the shape is too complicated, if we have too many support vectors that are supporting this complicated shape, this means that we might not be able to generalize as well, and this connects to the same topics we saw previously of overfitting and underfitting, and also to the idea of complexity and the bias variance trade-off. So SVMs are a powerful baseline, and we don't necessarily need to throw them away just because they were popular in the 90s and in the 2010s, early 2010s. If you have good features, which we'll talk about in a future module, and a thoughtful evaluation, often it's perfectly fine to use them. Here's our quick check. Here are the references we used. As always, thanks so much, and see you next time.